So we've built up to this idea of a sampling distribution of means, how means behave, and it's a really weird concept. It's hard to grasp. It'll take you a few times before you actually get this idea that this isn't real. It's a theoretical, hypothetical sort of situation of if you randomly sampled again and again and again from the same population, calculated the mean, got a different random mean each time, and then plotted those means, what would it look like? And a really good question to ask right now is why are we doing this? And we're doing this because remember, we want to talk about what's the probability of getting our data if some null hypothesis is true. And what we're doing now is building up sort of that background, that sort of this is what things would look like under a certain situation. And then we take our data, put it there, and say, what's the probability of getting our data or more extreme if the null hypothesis is true? And that's the definition of a p-value. That's what we're getting toward here. But we're starting to understand a little bit about how means behave. And so in the last video, we talked about what drives the sampling distribution of means. And we talked about the idea that there's two things that are important. One of them is the size of the sample. If you have a bigger sample size, the distribution of means will be much tighter because the highs and the lows will cancel each other out. And over time, you will get things that are closer and closer to the truth. So sample size is really important. The other thing that also drives it is how spread out is the population itself. When we talk about 2-year-old girls shooting basketballs, there's not a lot of variability in that. But if you think about, say, income, there's a lot of variability. So the standard deviation or the sigma or the spread of the population itself also drives how wide this thing is. The more variability there is in the population, the more variability you will get in your means. So we're going to eventually be able to draw a figure like this. And we'll say that's for a given n. I'm just going to make up a number here. Let's say n equals 36. If I took samples of size 36 over and over and over again, where would the center of that distribution be? Let's think about light bulbs for a second. If I knew the average light bulb, the true light bulb, the mu light bulb, the average light bulb was 1,000 hours, what would I expect to get for my mean? Well, you'd expect to get something around 1,000. Otherwise, you'd be saying, I'm taking a biased sample. I'm only picking the good light bulbs or the short or the long light bulbs. It's impossible. So you would expect to get something around mu. And so we say this, the mean of the means is the population mean. I know this is confusing, but think about it for a second. What would you expect to get? If it's unbiased, what else would you expect other than the population mean itself? So that describes the central tendency of this sampling distribution. The second question then is how spread out is it? How spread out are those means? How much will they randomly bounce around with noise? And the number we use to describe this is called the SEM, the standard error of the mean. And we've already sort of worked out that it's driven by two things. The first thing is how much noise or how much variability is there in the population itself. If you're measuring something which varies a lot, then your means will vary a lot. So in the numerator, in the top of this SEM, we get the sigma, the standard deviation of the population. And then in the denominator, we're going to see that it's driven by the sample size. A bigger sample, tighter spread. Now, there's actually a little twist that it's actually the square root of the sample size. I hinted at this before. Every piece of information that you get is worth less than the first piece of information that you got. There's sort of a law of diminishing returns when it comes to information. That this book, The 7 Pillars of Statistical Wisdom, really stresses that point, is that information has a law of diminishing returns on it. So that's why we see the square root. But the important point, the standard error of the mean describes the spread of the means. Now watch this video again. I know it's confusing, but we're going to build up in a minute and show you why the shape of this is such, and have a really good demonstration which will drive this home.